Welcome again. In continuation with the previous video, I'll explain about the design of synchronous counter using SR flip-flop, but this time it's going to be a random sequence, okay? Instead of having any mod counters like mod 4, mod 5, or mod 7, mod 11, mod 13, we're going to give a random sequence and then we'll try to design that particular counter, okay? So let's say the question is to design a counter which counts in this sequence. Okay, so it counts, starts from 0, goes to 1, then 3, 5, and 0. This is a sequence in which the counter is supposed to count, and we have to design it using, again, SR flip-flop. Okay, the procedure remains the same, the table will be the same. After the table, you are supposed to draw K-map and simplify, and then draw the final circuit. Okay, so we'll write again. In the table, what all we have is present state, next state, and outputs. So I told you what is the first step in designing? Identify how many bits are required. If you know how many bits are required, from that you can identify how many flip-flops are required. Okay. Now if you look at the sequence, which is the highest number in this? The highest number is 5. How do we write 5 in binary? 1, 0, 1. So which means I need 3 bits for this counter, which means I need 3 flip-flops in the circuit diagram. Okay, so if it is 3 bits, you will have 3 values in the present state, QA, QB, QC. Similarly, you'll have 3 values in the next state, QA plus, QB plus, QC plus. And in the output, you'll have, since you have 3 flip-flop and SR flip-flop, you have SA, RA, SB, RB, SC, RC. Okay, so all the titles are ready. Now we have to put values inside this. The first present state I told you, if it is 3 bits, you should write all 8 combinations of that in order. Okay, so all 8 combinations are written under the present state. See here, you don't have to worry about the question. If it is 3 bits, directly write all the possible combinations under present state. When you have to take care is, when you're writing the next state, that time you have to look at the given question. Okay, now in the question, okay, when I start, I'm starting with 0 now. If the present is 0, where should I go next? Do you have a 0 in the given question? Yes. So if the present is 0, what is the next value mentioned in the question? 1. So if present is 0, the next value corresponding to 0 should be 1. Now the next value, I have present as 1. Do you have 1? Yes. After 1, where it is going? 3. So after 1, it should go to 3. If a present is 0, next is 1. If present is 1, next is 3. Do you have 2 in the question? There is no 2 in the question. So if that number is not there, put X in the next state. Do you have a 3 in the question? Yes. After 3, where should you go to? 5. So after 3, it is 5. 1, 0, 1. Is there a 4 in the question? No. So X. Do you have 5? Yes. After 5, suppose in the question they have not mentioned anything after 5. It means that this is the last value. After it reaches the 5, it should go back to 0 default. Okay, whether they mention this or not, you please remember that if this is the last value, after that it should go back to the first value. If it is given, no problem. You can directly take this as a value. But if it is not mentioned, it is clear that after 5, the counter again starts from the beginning. Okay, so after 5, it should go to 0. There is no 6 in the question, so X, and there is no 7 in the question, so X. I hope this is clear now. If the number is given in the question, for that number, write the next value according to the question. If the number is not there in the question, for all those numbers which are not there in the question, put X in the next state. Okay, so this is how you write the table for next state when the random sequence is given. Now, rest of the things are exactly same as before. Using the help of with the help of excitation table, you have to write SR values for each Q and Q plus. Okay, so for the first one, QA and Q plus 0, 0. So this is 0x. 0, 0 again, 0, x. If you have x in one of the input, directly write x here. Next, 0, 1, excitation table, it is 1, 0. Again, you have x here, 1, 0, excitation table, it is 0, 1. And you have x in the remaining two. Okay. Same thing for B, 0, 0, 0, x. 0, 1 is 1, 0. Here it is x, x. Next is 1, 0 is 0, 1, x, x. And here 0, 0, 0, x. Remaining two are x, x. For the last one, it is 0, 1. So 1, 0. 1, 1 is x, 0. Here x, x. Again 1, 1 is x, 0, x, x. 1, 0 will be 0, 1. Remaining two are x, x. Okay, so I hope this is clear and I hope there's no mistake. Please verify it once. So this is how you get the table. Once the table is done, the next step will be to draw K-map for each of the outputs SA, RA, SB, RB and SC, RC. Since it is 3-bit, you will use 3-variable K-map. Okay. QA, QB, QC 0, 0, 0, 1, 1, 1, 1, 0. For SA 0, 1, for 2 you have X, 3 is 1, 4 is X, 5 is not there, 6 and 7 you have X. So here you get a quad. So your SA will be equal to QB. Okay. Next is RA. You can please pause the video, try to simplify it on your own, and then you can verify the answers. Okay. Please try to do it on your own, and then you can play the video and verify your answers. 1, 1, 1, 1, 0. For RA, you have 0, 1, 2, 3 is not there, 4, 5, 6, and 7. So here you can take either this as a quad or you can also make this as a quad. Okay, two options are there for you. I'll be using this as option. So my RA value will be QA. Okay, then comes SB. SB, it is 0, it's not there. 1, 2, 3 is not there. 4, 5 is 0, 6 and 7. So here you don't have an option for quad or pair. It's going to be a single value. There is no adjacent cell which is X. Okay, you don't have an option to group it with anything. It's going to be a single value whose answer will be QA bar, QB bar, QC. Okay, you cannot pair this and this. Okay, they are not adjacent. Coming to RB. QB is X0, X1, and all these are. Okay. So here you can make this as a quad. Then get RB is equal to QB. Okay, again SARB, you're getting the same answers. You have SC, SC, you have 1 X X X 1 X X X, and 4 is X, 5 is 0, 6 and 7. So you can group this, or you can take the four corners also. So I'll get SC as QA bar. And the last one, that is RC, will 4, 5, 6, 7. 4, 5, 6, 7. So here it is going to be, we'll get RC also as QA. Your RB and RA and RC are same. So you have all the six outputs now. The last step is to draw the diagram. 3 bits, so 3 flip-flops. All the clocks are shorted. This will do a count, okay? You can check the counter videos. Synchronous counter is going to do a count. All the clocks are shorted and given to a common input. This is SC, RC, SB, RB, SA, and RA. Then you have outputs QA, QA bar, QB, QB bar, QC, QC bar. Now your SC is nothing but equal to QA bar. So you just have to show a line with the value as QA bar. So you're done. RC is equal to QA. Okay. Then RB is QB. Whereas SB is combination of three values. And it is all into, right? Which means it is an AND gate. You have a AND gate which has three inputs. Three inputs are QA bar, QB bar, and QC. That is given as input to SP. Okay. And coming to RA, it is again QA. And SA is QB. If you want, since QB is here only, no, you can show a direct connection like this. QB to SA. Since it is right here only, you can directly connect and show that SA is nothing but equal to QB. Or else you can just show a single line and write the value QB also, okay? So your circuit is complete. So this is how you can draw the synchronous counter. You can design a synchronous counter for any type of question, whether it is a mod counter or it is a random sequence counter. The procedure remains the same. Main thing is, you should know how to write the next state. If you write the next state correctly and you know the excitation table properly, then this you can complete easily. Once this is done, simple K-map simplification and drawing the circuit. So this table is very important. If you make a mistake in this stage, then the entire problem is going to be wrong. Okay, so please be very careful when you're solving this part, especially the next state part. Okay, so that's it for this video. In the next video, I'll explain about how we can design a counter using other flip-flops. Thank you.